We really don't know where the cloud came from, but we do know that most of the material which is currently flowing into the galactic center black hole comes from stellar winds, material which is ejected by nearby stars. And it could be that this particular cloud also was coming from a star ejecting material, but happened to produce a very compact and directed right at the black hole. We're probing new territory. Here this cloud comes in, gets disrupted, but now it will begin to interact with the hot gas right around the black hole. We have never seen this before. We expect it gets hotter. It may even start emitting X-rays, very hard radiation, and then it gets disrupted, and then in the end, we expect it to fall into the black hole once it's sort of going through all of this churning. Now, we do know that galaxies have massive black holes, and these black holes grew over time from very small black holes to very big black holes. But this process of how material gets into and here in the galactic center, we have an opportunity, so to speak, to have a probe of this process, how material really gets added to the black hole and what the physical processes are, how the interactions happen in this very central region. That's a fantastic opportunity. Wir wissen wirklich nicht, wie diese Wolke entstanden ist, wir können nur spekulieren. Was wir wissen ist, dass das Material, was in das galaktische Zentrum hineinfällt, typischerweise von Sternen produziert wird in der Umgebung, die Material ausstoßen in sogenannten Sternwinden. Und es kann sein, dass diese Wolke auch in diesem Prozess entstanden ist, in diesem Falle aber sehr speziell, weil das Gas sozusagen sehr kompakt ist und direkt auf das schwarze Loch Die nächsten Jahre werden wirklich eine ganz fantastische Gelegenheit sein, die Prozesse, die passieren im Einfall von Gas auf ein schwarzes Loch zu studieren. Denn die Wolke wird jetzt nicht nur zerrissen werden von den Gravitationskräften, sondern auch in Wechselwirkung treten mit dem heißen Gas in der unmittelbaren Umgebung des schwarzen Lochs. Sie wird sich aufheizen, wahrscheinlich so heiß, dass sogar harte Röntgenstrahlung produziert wird und eventuell dann zerrissen und fällt dann in das schwarze Loch selber ein. Das ist also eine fantastische Gelegenheit, diese Prozesse sozusagen online zu sehen. Alle wahrscheinlich Galaxien ein zentrales, massives schwarzes Loch haben. Was wir nicht wissen, ist genau, wie diese schwarzen Löcher wirklich gewachsen sind. Offensichtlich muss Material auf solche schwarzen Löcher einfallen und das galaktische Zentrum bietet uns die Gelegenheit hier, diesen Prozess sozusagen in einem Labor zu studieren, was wir genau kennen und wo wir die Umstände genau kennen. Wir sehen also dann in diesem Falle, wie das Wachstum passieren kann in diesem inneren Akkretionsbereich, den wir bislang nur unvollständig kennen.
Hydrogen gas, the gas which we see anyhow in the galactic center all over the place. This particular cloud weighs more or less 3 times the mass of Earth, so it's a rather small and tiny blob only, but it glows very brightly in the light of the stars which are surrounding the cloud. The black hole, imagine it sitting here, has a tremendous gravitational force, and the cloud, as it comes in, it will be elongated and stretched. It will become essentially like spaghetti. It will be elongated and falling into the black hole. Wir beobachten das galaktische Zentrum seit nunmehr 10 Jahren mit adaptiver Optik, meistens um die Bewegung der Sterne zu sehen. Oder jetzt haben wir ein neues Objekt entdeckt, eine kleine Gaswolke, die Richtung schwarzes Loch fällt. Das schwarze Loch, stellen wir uns es hier vor, hat eine sehr, sehr starke Anziehungskraft. Die Gaswolke wird also Richtung schwarzes Loch fallen und dabei wird sie auseinandergezogen. Sie wird sich in die Länge dehnen und aussehen wie ein Spaghetti.
Astronomers using the new Atacama Large Millimeter Submillimeter Array, ALMA, have imaged a region around a young star where dust particles can grow by clumping together. This is the first time that such a dust trap has been clearly observed. It solves a long-standing mystery about how dust particles in disks grow to larger sizes, so that they can eventually form comets, planets, and other rocky bodies.
This is the ESOcast. Cutting-edge science and life behind the scenes at ESO, the European Southern Observatory.
Astronomers now know that there are plenty of planets around other stars. But many mysteries remain about how planets, comets, and asteroids are formed. New observations from the powerful ALMA telescope are now helping to answer one of the biggest questions. How do the tiny grains of dust in the surroundings of a young star grow, first to become rubble, and then even boulders well over a meter in size? Computer models suggest that dust grains grow by colliding and sticking together. However, when the bigger grains collide again at high speed, they are often smashed to pieces and sent back to square one. Even if they do not break up, the models show that the larger grains would be slowed down because of friction between the dust and gas, eventually falling onto the star without a chance to grow any further. Somehow, the tiny rocks need a safe haven, where they can continue to grow until they are big enough to survive on their own. Such a dust trap had been proposed, but never observed, until now. Astronomers used ALMA to study a protoplanetary disk in a system called Ophiuchus Infrared Source 48. This system is circled by a ring of gas, with a central hole that was probably created by an unseen planet or a companion star. Earlier observations using ESO's Very Large Telescope showed that the smaller dust particles also formed a ring. But the new ALMA view revealed that the larger dust particles were doing something quite different. Instead of the expected ring structure, a very clear cashew nut-shaped feature was revealed. This is a dust trap, a region where bigger dust grains